All right, let's get started. I was just trying to. Oh, perfect. Thank you. Whiteboard. Yeah. Thank you. All right. Hello and welcome to lecture 2. So this is the only lecture is going to be here. The rest will be back in the ELG 01. There is probably some event or something tonight. So tonight we are going to talk about images and image processing. I start with just a quick poll about your coursework. We initially announced 1st of May, and they said usually the coursework deadlines are on a Sunday. But because we have announced it before, we can do the 1st of May. So just a quick voting. Who is happy to have it on 1st of May? And, okay, 3 more days, right? All right, so it's going to be 1st of May, but look at it as like less than that. Don't imagine, because it's going to be the start of your exams, and at the time you will probably be, stuck with your stuff to study. So try to assume some earlier date for yourself so that those last few days would be an additional gift to you. So the Wednesday, 1st of May is the deadline, and lecture capture is also live on Moodle. You have probably seen that, right? Anyone had problems with it? So just go to Moodle, go to resources, and there is a link to lecture capture, and once you click on it, it opens a list, and you can select which lecture you are going to look at, and it's just about 2 hours each lecture, 6 to 8 usually. Okay, same problem we have. And it's going to be available. So tonight's also on lecture capture, but the camera is there. I don't exactly know where you will be visible, but probably that whiteboard is going to be captured. Anyway, I have some controls here. I can rotate the camera, but never mind. So just a quick recap from last time. First lecture, we talked about human visual cortex. We learned how the basic structure and perception takes place in our brain. So what the structure was, we had the retina, we had the cones, which were very, very important, and also the rods, which are also important, but cones are more important for color vision. And we said that all the signal goes through our retina, goes through the fovea, and then it goes through optic disc to the back of the brain, and then we had V1, V2, and so on. We had different layers. Yep. Next week I'll try another laptop, but I think this is a general thing with MacBooks these days. So we talked about the perception idea and said perception is not necessarily the same as sensation. And so, better? Yeah, okay. So we said perception and sensation are not necessarily the same thing. We looked at some illusions to see what limits of our visual system is. So many of these things will happen in the future lectures. We will see them, and we will try to connect with human brain to see where inspirations are coming from. Tonight, we are going to talk about computers and how they see images. We will start from very, very basic concepts of pixels, color channels, RGB, grayscale, HSV, and different color channels. We will see what they mean and how we can open an image in MATLAB, how we can read images, what rows and vectors, rows and columns mean, and so on. We will talk about some transformations. We will take a color image, convert it into a grayscale, and we will understand what is basically happening. And you will write your own Instagram filters tonight in the lab. So you are now expert enough to compete with Instagram and come up with your own filters to make images more beautiful. We will talk about some geometric transformations, and next week we will talk about more filtering. Now, so far we are just processing images. Next week we will try to extract information from images. So tonight everything is going to be about basic image processing. So in 1990s, usually a concert would look something like this, and nowadays it looks something like this. So everyone has a camera. We all have very good cameras on our phones, and everyone is constantly posting live videos on Instagram, trying to report to the world where they are. So cameras are playing a very, very big role, and we have a lot of data. And if you have a look at this chart, you see that there are millions of images being uploaded on a daily basis. But the problem is that once you are looking for a specific content in your images, you are usually you have to go through all of the images. You have to link it through. You saw a cinnamon roll somewhere, but you don't remember where it was, but you took a photo, and now you want to see that photo. So you have to go through all your photos, try to link it. Where was it? What time was it roughly? So go through. So you're limiting your search, and then you have to go through thousands of images and then find the photo you want. In computer vision, we try to come up with programs that can help us do that. You've seen someone, you want to understand or find out who that person was. So you're trying to see the face. You're trying to recognize the face, detect the face, and recognize it. So there are tons of images online. And it's as I mentioned last week, it's a very, very good market. A lot of companies have made millions and billions of dollars from these images. So we are going to learn how we can understand what's happening inside those images. And this is just media usage in an internet minute as of June 2018. So you can see in any minute about 4 million videos on YouTube are being watched. And like some other crazy statistics here. Nowadays, Snapchat is the main software that people keep posting images and photos on rather than other platforms. And there are millions of Google searches conducted. So these numbers are crazy. Imagine if you could make a penny from each of these views, how much money you would have any minute. This is why some companies like Google, Facebook, Instagram, which is now owned by Facebook, that's how they are making their millions of money. Any single ad that you skip on your phone when you're playing a game, you are donating money because they are just charging people for those ads. So this is the basic platform. This is marketing. This is the way money is being produced and sourcing all the infrastructure for having such a huge amount of photos. And you can, if you have like a hard disk on your computer, 200 gigabytes or whatever, 1 terabyte, going through those images and finding what you want takes you some time. But these companies are doing it so good that you just open your Facebook, go through the photos that you had 10 years ago, and you immediately see that photos loaded. So they have infrastructures that are crazy expensive, but they are making a lot of money with these views and clicks. So this is what justifies that investment. They are making so much money, but they are providing you a very, very good service for free, but it's not actually free. You are watching their ads, and this is how they are making their money. So there are a lot of different sources for consumer imaging. This one is nowadays a bit more obsolete, but we had digital cameras before. Every one of us had one, and we would take better quality images with them. Webcams. Nowadays, most laptops, iPads, iPhones, every device that you have has a tiny camera, which is referred to as a webcam usually, but it's no longer that weak. They're much more powerful. We have the GoPros, which you can use for sports. They usually give you a higher frame rate, so they have 120 FPS, frames per second. So the way they work is instead of capturing 30 frames per second, they capture, say, 240 frames per second, which nowadays most phones also have that. And then once you play that in real time as 30 frames per second, you see that action as a slowed down. So you can make some fancy videos with them. But GoPro, I heard last time, was filing for bankruptcy because not many people these days are using cameras anymore. Everything is in our phone. So a lot of devices are being replaced by the phone you have. There are other sources of cameras like security cameras, 360 cameras. One of the interesting uses of cameras is camera arrays, where they put an array of cameras to capture a scene from different angles. I think movie Matrix, which was a very groundbreaking movie at the time, they used these camera arrays, and then they would process those images and then do some video editing, and then you could see the actor standing, and then you could see from different points of view, and it was like a very nice visual effect. And smartphones. So nowadays, it's one of the, everyone has a smartphone almost, except those who hate smartphones. But any other person usually has a smartphone, and they keep taking photos and sending and sharing them. But there are other sources of images. They are not only bound to 2D images that we take on our camera. We have a digital photo, We have a thermal image. There are cameras that detect the heat, and they give you a heat map of what is around you. So these are used, they used to be used mainly in military when they were looking for targets among bushes where you couldn't see actually much, but the heat of the body of the person that you're following probably would give you where their whereabouts. We have other sources of images that use they have acoustic properties, and they work in different dimensionalities, like MRIs, like sonar scans, for example, like ultrasound videos. But generally, an image is a multidimensional signal that measures a physical quantity. It usually is a two-dimensional image as we know it. So we have an X and a Y axis. If we have time, then we have video. We have a three-dimensional image or a video. So let's see how we represent images generally in computers' language. An image is a multidimensional function. It can be a grayscale image, which can be expressed as a mapping from the set of real numbers in 2D space to the set of real numbers, which is brightness, if you like. So the images in grayscale usually show you the brightness level of every individual pixel. So we have X and Y coordinates, or widths and heights. And for every individual pixel, for instance, for this individual pixel, you have an intensity of pixel in the column or row, depending on the programming language that you use, 200 and 400, which is, in this particular case, X 200 and Y 400. And the intensity value is 178. Where do these numbers come from? What we do is, we are talking about computer language, and computers, as you know, mainly speak 0 and 1. So we have a bit, and the bit is usually 0 or a 1, right? So if you have 8 of them, what do we get? We get a byte, which is 0, 0, 0, 0, 0, 0, 0, 0 to 1, 1. And how many numbers can we represent with a byte? 256. How do we come up with that number? It's 2 times 2 times 2 times 2, which is 2 to 8, which is 256. So we can represent 256 different values with only 1 byte of data, right? So when we say that intensity value is 178, it's a number here which represents 178, right? So it's 0, this would be 1, and then you do the rest. So this is 128, and then this is 64, so this is also a 0, and then so on. So you will keep calculating which number you are talking about. So we have 256 different combinations that we can present with 1 byte only, right? So we will get back to those numbers, and we will see if we have 3 channels, RGB, what happens. So far, we are talking only about intensity or brightness of the image. So a basic digital camera usually has these parts. So you have a path of the light, you have the aperture to let the light in, and then you have a mirror which reflects the image on a pentaprism, which gives you a vision in your viewfinder. Some cameras don't have that, and you don't have that, but digital cameras don't have that. Your phone doesn't have this bit. And what it does, this image is reflected on a surface, which is a sensor. So how do these sensors work? We are going to watch a video to see what they do actually and how they represent an image. I think you know this guy. Let me see if I can give you... It's not working.
Okay. Anyway, the camera made it possible to make an instant picture in a fraction of a second, but the process involved it turned into a negative and then printed onto photographic paper in the dark. which was a problem with the rise of the digital age and the internet, and made it possible to make an camera made it possible to make an instant picture in a fraction of a second, but the process involved in getting the image out of the camera and printed was a complicated one. The light-sensitive film had to be carefully removed, sent to the processor, get developed, turned into a negative, and then printed onto photographic paper in the dark, which was a problem with the rise of the digital age and the internet, and your pressing need to upload a picture of Fluffy to the My Cat Looks Like Hitler web forum. But while the microprocessor revolution started to transform many parts of our lives from the 1970s onwards, the digital camera was a relatively late invention, arriving after the video camera, the mobile phone, the laptop computer, and even the Billy Big Bass singing plastic fish. This was because the technology that lies at the heart of it, the sensor chip, is unbelievably complicated. In a film camera, light is sent through a lens and a shutter onto photosensitive film, which, with a subject shot in normal light, needs just hundredths of a second of exposure to capture the image. The front end of a digital camera works on exactly the same principle. Light is focused through the lens and controlled by a shutter and a variable aperture. But instead of film, there's a light-sensitive sensor chip that has to record all of the data in a very short space of time. There are different ways of doing this, but we're going to concentrate on the CMOS, or complementary metal oxide semiconductor sensor, that now sits in the majority of digital cameras, from those integrated in phones to fairly chunky DSLRs. That's digital single lens reflex in the jargon. They're the sort that look like real cameras. The camera sensor is covered with tiny individual light-sensitive cells, each of which can measure the amount of light that falls on it. As the digital camera has evolved, so have the number of these pixels on the surface of the sensor. 10 years ago, you'd struggle to get a digital camera capable of delivering much more than a single megapixel of resolution, 1 million total pixels, or a grid 1200 by 900. But these days, 12 or even 16 megapixels are commonplace among top-spec prosumer and professional cameras. That's enough to enable you to produce images the size of a magazine cover with no loss in perceived quality. The cells act like the photosensitive chemicals on old-fashioned film, reacting to the light that falls on them and then reporting that to the camera's microprocessor brain. That would be fine for the sort of moody black and white shots favoured by gothy Instagram users, but because most of us want to post pictures of our lunch to Facebook in colour, it's also necessary to split the light seen by the camera into the 3 primary colours, which can then be used to create an accurate image. There are different ways of doing this. Some expensive cameras will employ 3 different filters, but most CMOS sensors will use what's called a Bayer filter. This is a grid of coloured filters that sits over the sensor with red, green and blue elements over individual pixels, and they will only allow their respective light colour through. Because the human eye is most sensitive to green light, which largely determines how bright an image looks, there are twice as many green pixels as red or blue ones. The filters are arranged in a clever mathematical pattern, which means that the camera's brain can interpolate using a demosaicing algorithm. Yes, really. Or, slightly plainer language, the camera doesn't just look at an individual pixel on the sensor, it also looks at the pixels around it to come up with an informed guess of what the true colour of that pixel is. Although, even the most advanced sensors in the world still struggle with the increasingly unlikely colour of Richard Hammond's hair.
Okay, so I wanted to skip the last bit, but it didn't happen. So this is generally the way cameras work. They have a sensor which has a Bayer pattern. As you saw, it's GRGB. So we are more sensitive to green light, so there are more green sensors in that. And for any pixel that we look at, there is a reflection of light on it, and each of these sensors starts to produce a number. And then there is an algorithm which extracts this information and produces an RGB value for that particular pixel, right? We will get back to it in a few slides again. So in order to explain the way cameras work, the simplest way is the pinhole camera model. So in a pinhole camera model, we assume that all light passes through a single point known as the center of the projection. So you can do this with a shoebox, for instance. You can just have a hole in a shoebox, and all of the environment that is in front of the shoebox is reflected on the other side of the shoebox. So it is the way basically cameras work. But how can we explain this projective trajectory is if you have a scene and you have a surface, which is, we call it image plane, or in that sense is your camera sensors, an image is reflected on that scene through this hole. So this hole is the central projection, and we have a focal length, which is the length of the focus of the camera. Depending on the lens that you use, this can be bigger. You can see, like you have telescopic lenses, you can see far, far away, and you have the smaller ones that you can just see focus on a very, very tiny subject that you're taking the image of. So this is the focal length of the camera, and then you have the different dimensions like I and J in your camera, and then in your environment you have X, Y, and Z. So how can we explain this? So you have the central projection, which is here, and the center of the image here. So if you want to put it in an equation, it's a very simple one. So you know that similar triangles, what we do here is we say y, the height of the image, the height in the image, over f, which is the focal length, equals to y, the height in real life situation, the height in 3D, over z, which is the distance to the camera in 3D. So basically, the further the object, the smaller it will be on your projection. So this is a very simple equation that you can use to explain this pinhole camera. But if you want to write it as a matrix, so we have the x, y, just put the w for making it into a matrix, x, y, w equals to fx, which is focal length in x dimension, and then you have fy, focal length in y dimension. Then you have cx and cy, which are the center of the image. And then you have x, y, and z, which are the real coordinates of the object in your image. So for every single point in your image, you can find a corresponding point in real 3D environment that you're looking at. This is called the intrinsic camera matrix, and questions have been seen about this in exams before. So S, oh, I see the pens now. So S is the skew, which just skews your images. We will play with these matrix, this matrix a bit tonight. So let's multiply it out. If we multiply these two together, we will have this matrix, which if we divide it by Z, we will have this one. So generally, the fundamental concept here is perspective projection is a divide by Z. So the further the object, the smaller, the higher the value of Z, the smaller the item will be on your image. So let's get back to what we talked about how images are captured on a sensor. So now the sensor is that image. Now we have a center of the trajectory, which is that point, that is the hole. We have a focal length and the environment behind it. So once light goes through the hole, it reflects on our sensors. These sensors they have different types. They have CCD, charge-coupled devices, or we have CMOS, which we saw in the video. There are different technologies for those sensors. But general idea is that there are small, tiny bits on them that they are sensitive to a specific lights. So some of them are responsive to green light, red light, and blue light. And based on the value that they produce, we get pixel value. We get the intensity in RGB. So far, we only had one byte, which used the intensity values from 0 to, if we go from 0, then we will have 0 to 255, because we only have 256 values, right? So they usually start from 0, which is, everything is 0, you see nothing, which means it's black. And once it's 255, it is white, right? So if I have only one byte, I get a grayscale. Well, what if I have 3 bytes? As we said, we have R, we have G, and B. So I have 2 to 8 here, times 2 to the power of 8, times 2 to the power of 8. What is this number? It's 2 to the power of 24. How big is this? It's almost 2 to 4, not almost exactly, 2 to 10 times 2 to 10. 2 to 10 is 1024, right? So you have, usually they just say 1K. So if you see a hard disk drive, it says it is 60 gigabytes, and once you open it, you actually see it is 58 point something. It's because of these 24s that you have here. So you have 1024 times 1024 times 16, which is, if you use these 24s here as well, you will have 16.7 million different colors that you can only represent with 3 bytes of data in a color environment. So, with only 3 bytes, we can represent 16.7 million different colors. And if our image is 12 megapixels, which means for each pixel we can have 16.7 million different values, you can do the math. What a huge number of different possibilities we can represent. But why do we have this number here? The amount of light that actually is reflected on a sensor is a continuous form. But our sensors have a limit. Let's say, for sake of argument, we have a small camera, like an old camera, a small resolution. The camera is 200 pixels by 200 pixels. It's a very, very old camera. It's not like a 12 megapixel. So a 12 megapixel is something like 3,000 by 4,000. So this gives you 12 megapixels. So if you have any number, you have to quantize it, because the signal that is coming is a continuous signal, and what you have here is a smaller amount, is a smaller size. Whatever the size is, you have to quantize your signal. So any information that is in that particular area in that scene that you're looking at has to be reflected on a tiny bit, which is 1 pixel here. So resolution comes in here. If I want to look at this image, this is a 480 by 640. If you zoom in, you will see something like this. So if your camera has a very, very high resolution, let's say 12 megapixels, then you can zoom in further and not lose information. But if your resolution is less, once you zoom in, you will see grids, because each of them can only have one value. So if you're looking at a very small resolution, you have a white, gray, black, for example, next to each other. But if you're looking at a better resolution camera, those bits are kind of closer to each other. So you will have white, white, grayish, 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 black, and then black. So you will see it smoother. So in order to solve this problem, we need to know what exactly we need from the environment. If we really need high quality images, if we want to print them especially on a poster, which is a big size, then we need high resolution. But if we have a low resolution camera, and like the real scene is like this, and our camera resolution is low, what we will see is something like that. Because each pixel can only have one value, right? So if your resolution is low, when you zoom in, you will see these grids. But how much resolution actually is needed? How much resolution do we need? Is it like the more the merrier? If I have like 800 megapixels camera, I'm going to be very happy? Not necessarily. It really depends on the job that you have in mind. For example, most of the state-of-the-art cameras now are using 12 megapixels or 16. They don't really go that crazy. They can. There are sensors that they can go like 40, 50. Nokia released the phone 2-3 years ago which had 40 megapixels camera, but nobody was interested. Because once the resolution is too high, storage problem is there as well. Because each of these images now takes about 3-4 megabytes to store. But is this number real? Do we really need that amount, 3 megabytes? Let's do the math. We have 12 megapixel camera, and each pixel is 3 bytes. 12 times 3, 36. megabytes. So each image should take 36 megabytes. But why do we have like 3 megabytes, 4 megabytes? It's because of compression. So these images, they are also compressed. We don't usually store the raw format, which is BMP. So if you have a very fancy camera and you're taking photos for a wedding or for a special occasion, they may give you the raw format, which you can do more editing on them. You can do more work on them. Those images are bigger. They are like, each of those images is 36 megs, 15 megabytes even. But usually these images are compressed, and we will talk about compression a little bit. We will not go through details, but we'll just talk about it later, next lecture, I think. So you have a rear camera of 12 megapixels on these devices, and the presentation is, if you have an HD TV, which is high definition TV, is the resolution is 2 megapixels. So you can imagine you have a 60 inches HD TV and it's only using 2 megapixels. It doesn't really need higher. If you have a 4K, you get a higher resolution. Yes?
I'm just curious how this compares to like an average human eye, or in terms of resolution, what's the kind of general?
Yes. To calculate that is a very difficult thing because the human eye is not something that is easy to just see how many sensors we have and what the resolution is. But most of our center of vision is on fovea. And the fovea area, the best estimate, there are different estimates. If you Google it, you will see a very wide range of numbers that come in. But fovea is about 20 megapixels. But if you go to the whole area in the eye, it's about 460 megapixels, the latest thing that I found. But it doesn't necessarily compare. It's not apple to apple. We cannot compare that because eye has a lot of different capabilities than a camera has. So a camera is probably able to capture the scene much more accurately, but we can interpret the scene with our eyes. So it's a different comparison. You cannot necessarily compare them. Yep.
In a similar way to how you're quantizing the image in terms of pixels, when you're sort of quantizing the color in terms of 256 per byte, is that more than the eye can see, or is there any advantage to say using more bytes per color channel?
Yes and no. This area is like if you look at it this way, let's say this is R, G, and D. So if you start from 0 to 255, we will have a 3D map of all of the colors that you can present. Many of these areas, some areas here and here, are not visible to us. We cannot see those values, so we don't see any difference. But there are some areas that if you have more clarity, if you have a better resolution, we will see better. Sorry, this is a color here. So there are areas that if you have more, but mainly they use more bytes for printing. So if you are using like a color format like TIFF, it uses 4 bytes. And each byte is 16. It's using 4 channels, and each channel is 16 bits, not 8. So those images, they kind of cover a much wider range. So you can see better print quality in the end because they are tuned to the way printers print. So a printer is also, they usually use color format CMYK. It's again, it's like yellow, black, cyan. And they usually use this color format for printers, which has like the tuners accordingly to the color, and they have like, depends whether you use jet printers or laser printers, but they all have their own different color format. So you can see that we do not usually need a lot of resolution. Even on an HD TV, even if it's 60 inches, you have HD quality, you are happy. You say this is enough. So 2 megapixels is usually enough. But the reason HD and 4K are expensive to broadcast is because it's a video. It's giving you that image 30 or 60 times per second. So you can do the math that if you have a 2-hour video on a 4K resolution and you do not use any compression, it's going to be a few terabytes. So it's huge. And 3D videos, if you have them, they have 2 different images that are fused together using the glasses that you use, and it's even double that amount. So if you don't use any compression, those videos are going to be huge and they won't fit on a DVD, on a Blu-ray DVD. So most of us are used to HD quality, and we cannot really tell that much of a difference between an HD and a 4K. And the rest is mainly marketing, trying to, because companies need to survive. So like Apple comes up with their display, which is good enough, and then the next year they come with Retina display, which is still good enough, and then the year after 4K Retina, and then 5K Retina, and like they need to sell, they need to come up with new things. But it is better, I'm not saying it's worse, but the difference is not that much, right? Anyway, so as discussed before, what we have is usually a Bayer pattern, which it looks at different sources of light. So we will watch a short video to see how this works. How does one sensor only see red, and how does the other one only see green, and the other one blue? But what happens is we have a demosaicing algorithm here that once it sees these things, it gives you a map. And then for every pixel, you have an R value and a G value and a B value. Then you can, depending on the color space that you're using, RGB, you can present color. If you look at the older TVs or even the LCDs, if you zoom in and you focus, like you focus and see the screen, or add some water, like drops of water on it, you will see these pigments. You will see green, yellow, and green, red, and blue. Because the way they also work is, now this is capturing, and that one is emitting. So what they do is they send a different light to different pixels, and in each pixel you have 3 different colors. So they send a different amount of energy to each of these different colors, and you see that individual pixel as, say, yellow or blue or white or whatever color it is supposed to have. So this is the fundamental of the way we store images, or we look at it. Okay, it's not letting me click on this. So
the light-catching buckets on a sensor are not really pixels in the traditional sense, even though we all refer to them as pixels. They are more accurately referred to as sensors, or sensing elements, or sensors which capture light. Most cameras today use something called a Bayer filter system. A complete Bayer set is made up of 4 color-filtered sensors, 2 green staggered with 1 red and 1 blue. Think of a filter as a very small piece of colored film covering the light sensor. Its job is to prevent certain types of light from entering. So let me ask you this. What do you think happens when different colored light hits one of these colored filtered sensors? If a red filtered sensor is exposed to a bright blue or green light, the sensor cannot see it. However, red light can penetrate a red filter, and the volume or the brightness of that light is recorded by the sensor. The camera's processor knows if any light penetrated the red filtered sensor, it can only be red, and therefore calculates that pixel as red light. So the color calculation happens in the processor, not by the sensor itself. Blue filtered sensors will only capture blue light, and green will only capture green. For the rest of this lesson, we'll use colored water to show you what the processor sees. Just remember, it starts out as an intensity of light, not a color. The information of red, green, and blue light, which makes up an image, is also referred to as channel information, or channels. Now I imagine you have several questions. You know that when you magnify an image, you see several colors, not just red, green, or blue, but you also see yellow and orange and aqua and purple and pink. So you're probably wondering, what in the world is going on? For every pixel we see in a digital image, 9 sensors are involved in the calculation. One central sensor, which would be the position of the target pixel, as well as the surrounding 8 sensors, which will contribute their information to the processor's calculation. Now, just for fun, say central sensor 9 times as fast as you can. That should keep you busy for a little while. Now, let's simplify this a little bit and instead look at 3 sensors, a red, green, and blue, with the middle sensor acting as the target pixel area. Now, we already know that if the sensors are exposed to red light, the target pixel will be red. If the sensors are exposed to blue light, the target pixel will be blue. And you probably already guessed that if sensors are exposed to green light, the target pixel will be green. Okay, now those were pretty easy. What about yellow light? Well, yellow light is made up of both red and green light. The red and green sensors both capture light, and the processor knows that when this happens, the target pixel is yellow. Aqua light is made up of both green and blue light. Purple light, or magenta, is made up of both red and blue light.
Okay, you get the picture. So this is basically the way we see or capture color. So back to the same question. If I have 1 bit per pixel, how many colors can I show? Only 2 colors, black and white, if I only have 1 bit, right? So your images are binary images. You will use these images most of the time in computer vision because they have most of the edge information. They are very, very small to work with. They are super fast, and they don't have the redundant information you don't need in computer vision. Not all of the time. In deep learning models nowadays, everyone is using color, 3-channel color. But previously, everyone was using this, and most of the time, this information is enough. So we have 1 bit per pixel, whether 2 to 1 is 2 shades binary image. If I have 4 pixels, 4 bits per pixel, I can do 16 shades. And if I have 8 bits per pixel, I can do 256 shades. So we say 0 is black, 255 is white, and then we have 255 shades of gray. So as discussed, if we have color images, we have 1 byte for red, 1 for green, and 1 for blue. So 8 times 8 bits here, so it's 256 times 256 times 256, which is about 16.7 million different colors, which is a very good estimation, back to that question, of visible range. But there are some values that are not exactly overlapping in this area. That is why there are different color channels. So depending on the specific task that you have, if you want to present something to humans, that's enough. That's good enough, like on a TV, on an LCD, or a printer, usually. But if you want to see the limits of human visual system, you would probably be better off with other color channels, like LAB, like we will talk quickly about. So what we do usually is we have these images. So for the intensity, for grayscale, we said we have I, X, and Y is one value, right? So this was the X position, Y position, and then you say something between 0 and 255, let's say 127. So this is a gray color. This is somewhere between black and white. But if you have a color image, the way we represent it is I, X, and Y, and the channel. So we have 3 channels. We have 1, 2, and 3. So usually 1 is R, 2 is G, and 3 is B. So you can separate those channels and show them separately. You can show red channel, green channel, and blue channel. And they don't look anything like this. This is just for illustration. You will see what they really look like. But this is combined. Once you present that image as a color image, you will see something like that. So how does human eye capture color. Back to lecture 1. We said we have cones in our fovea, in our retina, where they have different types. They are S, M, and L, the short, medium, and long wavelengths. So different cones reply to different rays of light, and then they have a different response, and we can capture, based on the responses that we get from them, we will see a color image. Our brain processes it for us. So again, for a color image, we show R, G, and B channels, and that's usually the way we do it in programming. We show it as a separate channel. So this is RGB color space, the three-dimensional space that we discussed. So the center of it is white, where this is transpose. The center of it is black, where R, G, and B, they're all 0. And then once every value is 255, the borders, it's going to give you a white image. So if R, G, and B are all of them 255, you will see a white image. We will do some exercise here. So you can come up with different colors according to the different values that your R, G, and B have. So a very simple one, 0, 0, 0, what color is it? Black. Next one, blue. Next one, green. This one. So you have a cheat sheet here, green and red, or green and blue, cyan. Then red, magenta, yellow, and the last one is white. So this is just the overlapping bits, but these can be any value between 0 to 255 as well. So if I have something like 255, 127, 0, it's going to give me the orange color. So you can represent 16.7 million colors with only 3 bytes of data. This is not the only color space. As I mentioned, we have different color spaces like HSV. This one is looking at hue, saturation, and value. So you have a hue of the color, which shade of color it is. It's a yellowish, greenish, reddish, and so on. And then you have saturation, how saturated this color is, and what is the value of it. Is it a very dark, that color, or is it a very light, that color? So again, you have the HSV color channel, which is more perceptually, it makes more sense to us because we are used to this more than RGB values in our daily life. You say it's a dark gray color. We don't say it's a 0R 255G. This is more natural to us in the way we represent color. So you can also convert an image from RGB space to HSV space, and you can separately look at channels. Again, this is just a very naive way of showing channels. If you look at them, actually, those hues and saturation values are not like this. Let's see. We also have the LAB color channel, which is based on the opponent theory. You remember we said in our brain we have some cells that are tuned to red plus, the opposite color, which is green negative. So they were like opposing colors. So here they have red and green, and magenta and yellow on 2 different sides, and black and white. So this is another way of representing color, which is called LAB. Again, this is more similar to what's happening in our brain than RGB space. And there are other sources of images. You have RGBD, where you also have depth. Like if you have a Kinect, or you're playing on your computer, you have a Xbox, for instance. It captures the depths. So it's a signal that captures the depths of the items, and you see a 3D environment around you. Your images have also depths for the objects. If I am here or here, the D value is different, so you can understand depths as well. We have different sources of medical imaging that they use different signals, not only color, they also use different sources of images. and also videos, which is an image over time. So it's also another sort of image per se. But as I said before, video is a sequence of images. So if you show 24 frames per second, you will not notice those images. Humans don't notice them as images. You see it as a moving object. In order to be on the safe side, most movies we watch are 30 frames per second, and our monitors, usually TVs, they refresh at 60 frames per second, so that you don't notice the refreshing of the LCD. If you are interested, there is a group on YouTube. They keep posting videos called, I think, Ultra Slow-Mo Guys, something like that. So what they do, they have different videos, and they have cameras which captures like 100,000 frames per second, and they just zoom in on a TV and show you what is happening. So in each frame that you see, every 30 times per second or 60 times per second, you see the whole TV screen refreshes. But because it is fast enough, you just don't notice it. You notice it as a moving object. Yeah, this is slow-mo, guys. So have a break, let's say 5-10 minutes, and then we will go with images in MATLAB. And we have to take some photos tonight, so if you need to powder your nose.
Sorry for bugging. I was just reviewing this here, right? So you're saying fx and fy are the focal length within the camera itself. So what do x, y, and w correlate through to the camera?
It's the coordinates in the go back. It's the coordinates of an image here, x and y, and then usually fx and fy are equal, but in some specific cameras they may not be exactly equal. So that's why we have two separate terms.
Perfect. And then there's two other questions for you with regards to this mosaic that's used here. It said in that video there they use 9 blocks, right, with using a green central block to determine the color that's going to be used for that pixel. However, there's only 4.
This is usually
associated.
4. Yeah, this is a Bayer pattern. The Bayer pattern is 4.
So does that mean then that pixels on either side of it will feed back information, and then there's
There is an
calculation
overlap.
done? Yeah, okay, so they basically do like an average value across the other 2 pixels to refer as a reference.
Yeah.
Okay.
Yeah. So there is an overlap. So 4, 4, 4.
Yeah.
But if you look at it as 9,
Yeah.
you will see that this 9, and then the next 9 starts here.
Yeah, yeah.
And then the next 9 starts
Ah, okay, right.
here. So in deep learning we call that a stride.
Okay.
So it's yeah, we will get to that.
All right, thanks.
No worries. Hi.
You earlier, I'm not sure if I got a chance to
I
read
did
it.
just yes.
I've got a chat tomorrow with right and I proposed a project for them in terms of I'm looking for something in computer vision. So they're going to be interested in probably just chatting through perhaps the project tomorrow. I just thought I'd perhaps give you a heads up to see if you were interested in
Yeah, I saw it. It is a very challenging thing
Yeah.
just to look at those images
That's what I
and
wanted to
try
see if you
to
had any input. 'Cause
yeah
it'd be useful to know.
see based on what the customer like whether they would like a new flap which looks like that, because those features are something that are simple to humans, but for a machine to say whether this image is similar to that is not that simple.
What I was saying, this is another thing, I'm not sure if, I mean, I was looking at something like Pinterest. If you stick in concepts like cozy living room, for example, it will give you images related to lots of cozy living rooms. So I was wondering whether was there any mileage in using something like Pinterest to sort of, as a
It is
developing a
definitely
training.
it is definitely interesting. But what I'm trying to warn you is that by looking at cozy images of a living room and say a modern living room or a the state-of-the-art living room, your model is not necessarily going to capture what you want it to capture. It may capture things that are like, in the end you will see like 60% accuracy, something like that, depending on the number of training images that you have seen. It is not going to be a groundbreaking thing that it just says 100%. It can give you some recommendations, but I don't see it as a, unless you have millions of images. Like if you have a lot of images and your model has seen all of those images, then it might be able to capture something that says this. So how do you define cozy? Is this a cozy classroom, or the last session was? It depends on which angle you look at it, how big it is, how much depth information you have. You know, there are a lot of different parameters that computer vision cannot necessarily see. So I wouldn't recommend it as a startup idea, because it is challenging.
For something like that, obviously you were saying that it requires a lot of images if you're going to try and have something which is a high level concept. So would there be mileage in just identifying more specifics? So I don't know, something like fireplaces, or even being able to understand something like I'm trying to think things which would be actual features that perhaps customers would be interested in. So things like these kitchens where you have a central area, just certain features that are more specific in terms of they're identified as objects as opposed to high-level concepts. Would that be a better start?
It would be, yeah. I like the fireplace thing idea. It's, because it's more feasible. If you have a lot of images of a fireplace versus a non-fireplace, then you can train a classifier to detect fireplaces, and then you can train an object detector to locate that fireplace for you, and then once there is an image. So, for instance, when I look for flats on Zoopla, the keyword that I enter is balcony, because I usually like my flat to have a balcony where you can plant, have some flowers and stuff, or barbecue. It's not illegal in that area. So this is the keyword that you can enter. So the problem is with the keyword is there are some flats that they do not have a balcony, but somewhere in the app the guy has said it is close to a balcony, but it is still pixel. Or on the other hand, there are some flats that they do have a balcony, but the advertiser hasn't mentioned it, and then I won't see those flats. So this is the problem with text search, because they need to have manual tagging. What I suggest for you, Gigi, is to look at images and find these features. Say this flat has a dishwasher, and then find it in the images that they have provided. So you train dishwasher is a bit tricky because, well, anyway, you probably could do dishwasher. Yeah, that's a tricky one because it could be a covered one.
Could be behind the cover.
Yeah, but something like a fireplace is, that's why I like that it cannot usually be
I
covered.
mean, the other thing is, things like spotlighting is another example of something where perhaps it's the same thing as if you're looking for a specific feature which is actually generally something quite recognisable and it's quite unique. And it's also something which customers quite like. In terms of
If you have a photo of the lights, maybe, but otherwise it depends on the images that have been provided for that particular flat. So you're very much bound to those images that you see. So what I see here as a feasible project is to look for objects like washing machine. Usually flats have it, so it's probably useless to do that. To just see if it's furnished or unfurnished, which is again another tag.
things like heavy carpeted and wood flooring.
Yeah. This could be. This is a good one. Fireplace is a good one. Balcony might be a very tricky one, but maybe a good one.
I like a little thing. I kind of understanding more of the concept. Because I guess the idea originally was a high-level approach of having almost a recommender system eventually based on the images. So you have an image which is...
This would be a further down the road thing.
I
So
guess
once they say, I like this flat, then you will see what is in the flat, and then match the ones that have that in the flat, and then show it. But if somebody likes a flat which is I don't know, maybe the location. I like this location, so this is the flat that I like, this is the location. And I think that there are a lot of different parameters, not only computer vision. Computer vision is a bit of it. Once you come up with a result, then it has to be merged with other features and then sent to the final classifier.
My whole rationale was because when I rented initially when I was recently bought my place with my wife, we went through the images, like hundreds and hundreds of images. They're not, obviously the geographic location and price is important, but once you've got your list, you've got the images to go through, and that's why I was thinking some sort of communication approach.
It is not that easy to do. I'm not trying to discourage you, but I'm also trying to warn you.
This is why I wanted to see if what I was proposing how it helps frame it.
I think going for objects rather than the whole concept as a start would be a better idea.
That's really useful.
All right. So, images in MATLAB. MATLAB, also known as Matrix Laboratory, is well suited for images because it basically works with matrices, two-dimensional matrices, and it is a very good fit for images. So images are usually two-dimensional matrix. And we can have three of those matrices next to each other to represent R, G, and B. The way annotations in MATLAB work and the way you can present an image is there are some functions built in, and they are very, very easy to implement. So you open MATLAB and type imread and give the address to the file that you wanted to read, and it automatically loads it into your environment. So once it is loaded, you can use imshow, which shows the image. So most of the image functions in MATLAB start with im. So imread, imshow. It's usually that simple. Imrotate, imtranslate, and things like that. Imresize. So imread loads the image, or you can use the load function as well, but that would be a bit different. This one looks at it as an image. Then you have imshow, show the image. Once you have loaded your image, you can also use variety of different extensions. So as I mentioned before, the images usually have a BMP extension, which is bitmap, but that is a very, very space-consuming format because it is in its original values, and we usually have compressions. So JPEG is Joint Pictures Expert Group, something like that. That's a compression format. And for videos, you have MPEG, Moving Pictures Expert Group. You have different formats. You have JPEG, you have TIFF, you have GIF, you have PNG, and each of these compressions have their own pros and cons. JPEGs are the most common on any computer, and MacBooks, Mac iOS basically usually likes PNG format. PNG is better for text. JPEG is better for natural images, but you will see the differences. You can convert your images, you can save it as a different format and see what they look like. But anyway, you can open an image, greens.jpg. There are some built-in images in MATLAB that you can just load and start playing with, like cameraman, like a lot of other coins. There are some basic images so that you can play with. But you can start with your own images. Just take a picture, load it in MATLAB, and start working with it. As I mentioned, you can show separate channels. The way you do it in MATLAB is I am show I column 1. So this is showing all rows, all columns. And then the channel number R. If it's 2, it's G, and if it's 3, it's B. And if you just put another column here, you will see the RGB image, all of the channels. And if you want to see a specific range, you just say, I have this image, and I want to show just this bit. You just show I, say, 20 to 40, 60 to 80, and everything. So this shows you that cropped region according to the locations that you have. So this is 20, 40, let's say 60, 80, right? So you can show that cropped region in the image that you have. Images, as I mentioned, are usually uint8, which is unsigned integer 8 bits. They have the formats like this, uint8. And they show 256 different values. But when you're processing your images, you're trying to apply a filter on that, you usually don't like integers. You prefer real numbers. You want not to lose the accuracy. So if you have a pixel and the value, the multiplications that you have, it gives you 0.7. Integer is automatically converting it to 1. And if you have 0.6 or 0.9, it's always converted to 1. Sometimes you need more accuracy than that. Then you can convert your images into double precision. You will get a floating point. You will have real numbers. Not real, but not integer. So you have double values, and you can convert them. But beware, if you do that, once you're showing your images, if you're showing a double image or you're showing an integer image, they are different. Because if MATLAB thinks your image is unsigned integer, and then you're showing it the double values, once you convert it to double, the values are between 0 and 1. So the range you have is 0 and 1, and for integers it's between 0 and 255. So if you have a double image and you show your values are 0.43, 0.85, they are either converted to 0 or 1. And what you see is something like this. So it's not that real image that you have. So once you're converting your images, everything over 1 is 1. If it's looking at it as a double image. And everything under 1 is 0, which is why you get a funny image. So in MATLAB, there is a function called im to double. It automatically converts your images into double. But if you don't want to use that, you can read an image, convert it to double, and then divide it by 255. And then you still get the proper image. So this is just a technical hint. Once you are programming, always from time to time look at your images. See that you are feeding the right format, the right sizes, the right scale to your algorithm. Because if you don't do that, it might waste your time. You have to be careful with that. If your code doesn't work, oh my God, this is not working. His code is working, mine is not. You might see something as simple as that. You haven't divided by 255. And now your code is looking at everything as 1, and nothing works. So you will panic, and you don't want that. Anyway, you can do color space conversions in MATLAB very easily. So the function, for example, you can load an image, and then RGB to gray just converts it to gray for you. And gray is an average of RG and B channels. So if you want to write the algorithm yourself, you can just say, read each channel, add them, divide by 3. So this is how gray is calculated. So RGB to gray, just one function, does the job for you. You can convert your images to HSV channel. So we will play with that a bit today. So load an image, then say RGB to HSV. You give the input image, and then you have the output image here. Here you can see separate channels, but again, these have nothing to do with the actual hue, saturation, and values. They are just showing this as a grayscale image, right? So you see those images. Then you can convert it back, HSV to RGB. But what we do is once we get these channels, we can work with them. We will see that. If I get HSV channels and I want to make my images a bit lighter, darker, I want to reduce intensity, increase intensity, make my images a bit more purplish, more reddish. These are the things that you can do once you work with individual channels. And this is how Instagram-like filters are working. They get the image, they take channels, and then they apply some filters, which is increasing redness, reducing blueness, and things like that. And then the image you see finally, okay, I like this most, and then you post and share that. So there are some imperfections in imaging. One of them is limited resolution. As we discussed, if you have this image and you have a low resolution, it might look something like this. You will see grids, which is not optimal, but depends on the task that you have in hand. In most computer image works, we do not exceed resolutions of 500 by 500. We don't use 4000 by 3000. That's too much. Because if you want to process those images with that resolution, you see a lot of detail that you really don't need. You remember that example from first lecture? You could read that text even, there was all those problems and errors in it. The features that you need are not in these details. You don't want to work with that, but this is most likely enough to tell who this person is. And if you have this, then good. But if you have something super high quality of the same person, you're probably only wasting resources, right? So we don't go for super high resolution images. And the images we take, we usually resize them. For example, most of the deep learning or machine learning methods, they need a fixed input size. So all of your images have to be the same size. And they usually reduce it. Like the images I worked with in my last paper was like 544 by 544. And the reason is that was divisible by 16. So it's a simple number. And I use that number for object detection and segmentation, classification, and things like that. And that is usually enough. There are other problems. You might have noise in images. You might have bloom. Next week, we will learn how to remove noise from images. We will run high-pass and low-pass filters on images. They are very simple. You will be surprised. There are other sources of problems in images: motion blur, poor contrast, compression artifacts. When you compress an image too much, sometimes you lose detail, especially on the borders, which is more visible to us. You may have lens distortion. Depending on the camera and the setup that you have, you might lose some information. So what does digital image processing do? Digital image processing is the use of computer algorithms to transform an image. So you can transform color, you can have geometric transformations, and then you can do filtering. As I mentioned, one of the filtering things that we do is reduce noise in images. So what we do is we have a kernel, very simple kernel, which is a low pass or high pass. Then we multiply it over the image. This is called convolution. So convolutional neural networks, they are basically a kernel that you multiply on an image several times. So we will get to that. So tonight, let's talk about color transformations. Brightness transformation is once you have an image and you want to make it lighter or darker. What do we do? I have the values, intensity values, and I want the image to look brighter. I add 20 to each pixel, right? This way the image is going to look brighter. And if it is over 255, I cap it at 255 because I cannot show more than 255. So this is a very simple way to make the image look brighter. But is it smart? Do I want a better way? So let's start with a very simple way to process images, to see what image processing would mean. Negative of an image. You have J equals 255 minus I. What does it do? If the value is white, which is 255, it converts it to black, 0. And if it is 0, it converts it to white. So it's giving me the negative of the image, as simple as that. So if you have an image like this, the negative of it in a color space would look like that. And again, in MATLAB, it's very simple. I equals I am read, j equals 255 minus I. If you don't want to use MATLAB, this line would be two nested loops, right? So you would have to go something like this. For I from 1 to, let's say the image is 400 by 400, or 400 by 600. And then you will have to go extract the value of each. Let's say 10 is image. This I is different with this I. Get the value. Then I say 10.2, just a very bad way to talk anyway. And I say 255 minus 10. And then I say j, ij is 10.2, then n, and n. So this is this line. If you want to do it without, like you want to do everything yourself. And this is much faster than that. Because MATLAB has optimized its functions. So if you call functions generally in any programming language, always try to avoid nested loops. They are very slow. Because it has to, go through all the processes. You could eliminate this line and just put it here. So you could just put this bit here, replacing that. It would make it a bit faster, but anyway. So for most of the things that we can do, and they are going to be done quite often, MATLAB has already done it, and you can just call the function, right? So now we did a very basic image negativating, whatever. So tinting, if you want to change the colors, like make the image look more red, you want to make it look more blue, you can come up with a matrix like this. So for every individual pixel in your output image, you have this matrix multiplied by every individual pixel in the existing image, and it gives you the result that you want. So what does it look like? If I put 1, 1, 1, the output image is exactly the same as the input image. But if I put 1.3, I'm making the image look more red. If I put it like 0.7, I'm making it less blue. So let's have an example here. I'm reading an image. This kid is a success kid. Do you know the story about it? The father took this photo. It looks like a determined kid. And they made millions of dollars by copyright of this photo. So you have to have lucky. Anyway, yeah, the kid is now grown. Nobody likes the photos anymore. But when he was a kid, this photo made a lot of money. So it's copyrighted. I think it's 2004. No, I think so. I'm not sure. Just a rough guess. But yeah, they made millions of dollars with this photo because it looks determination and things like that. Anyway, so we call it Success Kit, and so you have RGB channels. R is all X and Y, first channel. G is all X and Y, green channel, and then blue channel. So what I'm doing here is I'm multiplying the R channel by 125 and leaving these as 1, doing nothing, and then showing it. So now I made the image look more red. So I increased the red in the image, right? What about HSV channel? I get the image, load it, convert it to HSV channel. MATLAB has it built in, super fast. Extract HSV channels, and then what am I doing here? I'm reducing saturation and leaving value and hue the same, then putting it back into the image, and then showing it. So you see, the second one is a less saturated image, right? As simple as that. So how do you darken the image? Yeah, you can reduce value. Make it 0.3, for example. The image will be dark. So some guys came with this idea of doing this on images, and they started Instagram. Okay, you're a bit late. So the next thing is the histogram of the image. So histogram gives you the count of intensities in the image. So what we have here is an image of some used to be fancy cars, and then you have the histogram of it. So as you can see in this histogram, this is showing me number of pixels that have a specific value. So it's from 0 to 256, and it's telling me that like 500 pixels have value about 100. About 1500 pixels have a value between 150 to 200. So you can see this image is a bit washed out. It doesn't have a distinct black and white in it. Most of the values are between 100 and 200. It's not using the full range. So by drawing the histogram, or in MATLAB IMHist, it automatically shows you the 256 pins that you have decided to have for this grayscale image. How can I use that? There is another way to look at it. Let's look at it as a probability distribution function. You can think of this histogram map as how likely is it to have a pixel value that has a color of 150, intensity of 150, and it gives you a number between 0 and 1. So it gives you a probability distribution. You can also look at it this way. And this is just a simple code to show you how you can make a plot in MATLAB. So you just say whatever variable name you want to give it, PDF or whatever, probability distribution function, equals to h over sum of h. So it just calculates the whole matrix sum. Because this is a figure, you show it, then plot, and then put title, X label, Y label. There are a lot of different ways to show images and plots, and you can just go to MATLAB help. The good thing about MATLAB is that it is run by one company, so they have a very organized way of support and help, and everything is online, and you can just type in MATLAB help, plot, and it will bring a list of things that you can find, or you can just go to Google, just type plot help MATLAB, plot MATLAB, and it opens the home page for that function, and you will see a lot of useful information. So you can do this, and it gives you a probability distribution. So now that I have the idea that everything that I have is between 0 and 200, I want to stretch it. I want to stretch this range to 0 to 256. It was between 100 to 200. I want to stretch it. I can do something called contrast stretching. So what I can do is I can say j equals to alpha I plus beta. What it gives me is I can say multiply the values by 2 minus 200. So that I have something in the range between, it was 100 and 200. Now I'm getting it to the 0 to 256. And then I convert it to unsigned integer and then show it. So you can see what a big difference it made, just equalizing the histogram. There is another way of doing it. It's a gamma correction. But to come up with those numbers, 2 and minus 200, it's something that I did. If you want to come up with it yourself, you have to find a way to do it automatically. Another way we can do is gamma correction. We will talk about it automatically. Another way to correct images is gamma correction. So you have an equation like this, and so instead of multiplying and adding or dividing, deducting something from that, you can just do something like this equation. So I say gamma 2, and then j equals to this equation, and show it. So it is another way of making your images look nice. So again, as I said, this is just you take your image and you take it to any power of any value that you have, I to the power of gamma, which in this case is 2 that I came up with. It's not calculating it itself. I decided that the value of 2, I tried different values and I realized that 2 is better. So in Photoshop, you can get a bar and play with it to see different values, what your image looks like. So far, we are just processing images. Nothing is automatic. Everything I decide. It's try and error. I just decide that if I take the gamma value to a specific range, my image looks nice. And then you just multiply your image. So this is my image, double I to the power of gamma, and then multiplied by A. Yep. So the automatic way of doing it, one of the automatic ways, is called histogram equalization. So what I do is I'm trying to achieve a flat histogram. So instead of having everything in the range of 100 and 200, I want to make it flat. I want to just flatten it. So what I do is I use the cumulative histogram. So H is imhist, which is a function that MATLAB has. So I draw hist and then divide it by the size of the image and then show the PDF. And what I do is multiply my image 255 times CDF of I plus 1 and then show the image. So in MATLAB, again, there is a function for it called histeq. So it calculates the equalized version of your histogram. So now the histogram looks like this, but the image looks like this. It is not as nice as we did manually. That's why always the automatic methods do not look desirable to the eye. Sometimes you like a filter on Instagram and you don't like the other one because they are using some structures behind it. Yes?
You don't meant to like one over range and then start calling back.
Yeah. Okay, so we did some basic color normalization, make the images, look a bit more red, less red, brighter, darker, more saturated, less saturated, and equalize the histogram to correct the images. But what else can we do is geometric transformations. Let's say I have an image like this, and I want to have something like this. This is other sources of distortions that I have, like the camera, the lens that I had wasn't really perfect. I have taken a photo of a driver, the driving license, the registration number, and that number is not really looking good. So I want to rotate it, fix it, and be able to read that number. So here we are looking at geometric transformations. What we need for geometric transformations, again, is some points in the correct image and distorted image. Again, nothing automatic. We are not that advanced yet. Lecture 5 will be automatic, right? So far we are learning how this can be done manually, and later we will learn how we can do this automatically, how we can actually extract features, how I can say this bit is this bit. Now I'm manually selecting it. So geometric transforms also have a form like x prime equals to transpose x. So we are transforming something, transform of x. We are transforming something from one space to another space. So what we need to do is we need to transform every location. So far, we have been working with intensities, with values of the pixels. But here we are talking about locations of the pixels, right? So where should this pixel be? I'm not changing the value. I'm not making it lighter or darker. I'm just saying the pixel 1020, whatever value, in my new image should be pixel 510. So this is geometric transformation. We are no longer dealing with the intensity values. So we need an image warp. And in order to make this, for every pixel position x prime in the corrected image, using transpose of t, I need to determine x, where x came from in the distorted image. Interpolate a value from ix to produce jx prime. So as you can see, the best way to do it is I have the new image, I have a function that has converted the old image into this, but if I want to calculate this function, I go the other way around. So we are doing this backwards, rather than using a forward mapping T to transform pixels from the distorted image to the corrected image. We use the inverse transform. If I transform this image, the existing one, to where I want it to be, I may end up with gaps. So this may end up here, and then this one may end up here. There might be gaps, so I will not have a value for these gaps. But if I do it backwards, for the image that I want to have, I want to see where this pixel was. So this is an inverse problem. If I write it as a function, the affine transform is something like this form. So we have a set of values that are multiplied into our existing values. Again, these are x and y. These are locations. So something has shifted it, rotated it, translated it, right? And then has resulted in this new value. So MATLAB, instead of doing this for every single point in your function, you can use MATLAB affine 2D, give it a few points, and then it creates a function, a matrix for you, which you can use IM warp to later convert those images. Don't worry, you will understand. So let's take a look at some simple cases. I want my image rotated. Very simple thing we keep doing every day, right? You have an image, you want to rotate it. What do we do? If I want to say for every individual pixel in this image, find a mapping in the rotated version, there may be gaps. So I say the rotated version I have by 45 degrees, I know that each pixel in the rotated image should come from where in the original image. And then I multiply this function into the values that I have originally and then create that map. And then just put those values where they belong. And then you have a rotated version. For rotation, for example, you have this equation. These are the values that come into the matrix. For scaling, you have something like this. So what does it do, basically? It's just saying if it is like a number 0.5 and 0.5, it is saying that every position that I have in the new image should take half of the position of the existing one. So it just eliminates some existing pixels and put those, if I have a position 100 and 100, it will locate, find that pixel value, put it in 50 and 50 in the new image. So this is scaling my image down, right? So if I want to rotate it, I find these parameters of the angle of the rotation. If I'm going to rotate it, say 90 degrees, it finds these values, finds where this pixel should be, gets the value, and puts it where it belongs. Let's look at some examples. Again, because these three are very, very common, MATLAB has functions for them. IM translate, IM rotate, IM resize. Then you can say what scale you want. IM resize, your input image, and 2. And a new size that you have in mind. 544, 544. You have to look at the help section on MATLAB to see what parameters each function accepts. Let's have an example. I have an image here. I am read holiday.png. I am show I. So I have this image, read and shown. I am translate I, 100 and 0. It shifts my image 100 pixels to the right. So you see you are missing some stuff that you had here, and you see some black here. So it's shifting it 100 to the right. I have this one, IM rotate I45. It's rotating the image 45 degrees counterclockwise. And then you have scaling, IM resize I1/2 or 0.5. You get smaller version. Yep. So so you can play with that matrix. You can play different parameters. If I put this value in it, or the skew value, it's going to skew your image. So all the locations are going to be skewed. But what is the use of these transformations? Why do I want to do that? Yes, sometimes you want to resize your images. You want all of your images have the same size. So what you don't want is to just cut some part of your image. You want to see what values were in the borders anywhere in that image, and then map it to a smaller size or to a bigger size. Another example is like this that I mentioned. You have a license plate image which looks like this. So you want something like this. Again, this is manual. These numbers are not automatic. So I read the image, show it, and then decide that minus 15 degrees rotation is what I need because it looks like that. So I want it to look like this. So I rotate it 15 degrees clockwise. And then now I need to skew it. So I skew with the function that we had, I.30010001, which is this function, this one. So 1, skew, and then the rest is 0, 0, 1, 0. So I have exactly the same thing. 1, my skew is 0.3. Again, I manually came up with this number. I know that this is probably 0.3. I tried different numbers, and I realized that this number is the best. But when I go to lecture 5 and 6, then I will find better ways instead of manually doing it to do this. So 1.30, and then I get a very nice looking registration number. And if this guy has been speeding, good luck. Now I can read the plates. This is some of the things that are done once you speed. So this is a small exercise for us to see that we understand these affine transformations. So this is the main matrix that we talked about, and depending on the values that you have here, you are doing different things. So let's start with the first one. Which image do you think it is? I hope I haven't given you the answers. No, I haven't. Okay. So what I do is I create a reference image, IMREF 2D 700 by 700, so that I can show the changes. I don't lose the corners and the cropped area if it exceeds the existing image boundaries. Then I create this affine 2D. So I'm doing 0.5, 0, 0, 0.5, 100. So this 100 is already telling me that I have 100 here. What is it doing? It's shifting the y 100, or shifting x 100, shifting y, right? So it's shifting y 100. So this one would either be B or A, right? Because it's shifting 100 the y dimension. So this is x, and the height is y, right? So it's shifting it 100 lower. So it's either this one or this one. So I have 0.5, 0, 0, 0, 0.5. Let's look at the cheat sheet we had. So it's not a skewing, because a skew is these two are 1. What else could be? Yeah, it could be rotation. Right? So it is 0.5, 0.5. What about this one? 0.5, 0.5. So it's a scaling, right? So this one is this one. So do this one a bit, play with these parameters, do in your spare time in MATLAB as well to see what these changes actually do. Some questions have been seen like this. So, but let's say I have some points. I have the corresponding points in the image that I have and the image that I want to have. I know that this point is this point. This is the image that I want. I manually rotated the image in Photoshop and I thought, okay, this is what I want to have. Okay? So this point, I know is this point. I know P3 is Q3. I know P2 is Q2. And I know P4 is Q4. So what I need to do is I have 4 points, but I need to write a function that can translate this image to this image. So from 4 points, do it for the rest of the points. So we are now estimating through correspondences. So you can open an image in MATLAB, just look at the points. So on each point you click, it shows you the X and Y and the RGB values if you have this tool selected. So it shows you the value of that point. So I know the value of these points and their location. I don't care about the values at this stage because I'm just thinking about location. This is a transformation, projective transformation. And this is the beautiful matrix that you will need to solve. And questions are not on the exam. So what you need is you have 3 points. And this is the function that you have for affine transformation. And this is the output that you already have. So what you need is you need to solve this equation. If you have more than 3 points, you can use pseudo inverse. But anyway. Don't worry, you don't need to do this. This is the way you can do it in MATLAB. So what you do is you read the image, you manually select a few points and their corresponding points, and then you say this is your M function, which is this matrix. Then you define that matrix. A equals inverse M times Q, and T form equals affine 2D, and then warp it. So MATLAB does that for you. So all you need to do is find those points, give it this function, calculate the inverse of it times Q, and then affine 2D A. But again, making it a bit simpler, just give it the points and call the function estimate geometric transform. And MATLAB does the rest, and then you just warp it and show it. Manually. This is nothing automatic here. You just open you just create this image and you say this is what I want. So imagine in an imaginary world that all the plates that your camera is capturing look like this because of the angle of the camera on the road. So you take one plate, you edit it in Photoshop, you create this, and then you manually find the corresponding points. Later, we will find automatic ways to do that. All right, so this is estimate geometric transform function. And here I'm telling it it's an affine transform, which is the sort of transformations that we have seen. And then warp it and show it. Perfect. So it just with 4 points, it rotated my image. So we have different sources of projective transformations. Now, so far these two were 0. They are no longer 0. They can be also values. So we can now estimate transformations with more degrees of freedom. Something like projective transformation. So if I have an original image like this, the affine transform converts it into something like this, but the projective one converts it into something like this. So the difference is in this yellow brownish bar here. So this is what I have originally, or the red one. So you see in an affine transform, this red is converted into this brown is converted into this. But I want this to be converted into this, so I'm making it a square. So I'm creating a projective transform. So projective transform, as you can see, there are some projective issues in this image. So I want to make it a square. It needs 4 points rather than 3. For previous one, we only needed 3. For this one, we needed 4. So here we are going to have a bigger matrix. And again, in MATLAB, we can just call estimate geometric transform function. But here, instead of affine, we call projective. So this is the hierarchy of 2D transformation. So this is what we talked about. And this is the hierarchy of 2D transformations. We have projective one, which has 8 degrees of freedom. We need 4 points. And then we will be able to find collinearity as well. Then we have affine ones, 6 degrees of freedom, parallelism of lines. We have similarity, 4 degrees of freedom, ratios of lengths, angles, and rigid body, 3 degrees of freedom, lengths, and areas. So this function can help us to translate one image to another one in a spatial domain. The previous one, in the beginning of the lecture, we helped in intensity domain. We worked in intensity domain. We made images look brighter, darker, and now here we are shifting the location of the pixels, right? So these are the there are other nonlinear transformations like radial lens distortion, non-rigid transformation. Again, they have, you need to estimate that function, but these are not as simple as that. They may need a bit more work, and you don't need to worry about it. But what we need to do is to understand what IM rotate does. Once you rotate an image, what is the process that is going behind it? Nowadays, computers are so fast that we don't notice these changes. But anytime you're rotating an image, all of these calculations are happening behind it. Anytime you open an image, because most images are in JPEG format, JPEG format doesn't look like an image. There is a software behind. If you have an old computer, you will see that once you open an image, it takes a while to load it. And then when you click next, it's quick. It shows the next one. But if you go back, it takes a while to load the back one. Because they are trained that once one image is loaded, then start automatically loading the next one. But nowadays, computers are so fast, you don't notice these things. But once you have a JPEG image and you're opening it, there is a lot of processes going underneath. It's converting that JPEG into BMP and showing it on the screen. Once you're rotating an image, all of these processes are happening. Once you shift it, scale it, zoom in and out on your phone, now you can do it with 2 fingers. So now you know what happens. So all of these transformations are happening. Multiplications of matrices is basically what's happening. Computers, mobiles, are using parallel processing. They have several cores, and they make these things look really, really smooth and fast, and you don't even notice all of these processes that are taking place. So, good news, the coursework has been released, and you have until 1st of May to do it. The coursework is, the reason I have decided for this coursework is because it starts from scratch. It gives you a real hands-on experience. What we will do is we will take a group photo, all of us together, from different angles, different points of view. If anyone doesn't want to be in it, that's absolutely fine. But if you are in the group photo, please stay for the individual photo as well. So what the coursework is, it's a very fun one. People love it, except those who don't do it and they keep complaining. So what is going to happen is we are going to take a group photo, all of us, several of them, different angles, different viewpoints. Then we will go to the lab, and each of us will hold a number. So I have numbers from 1 to 100, and then we will have a mock shot. So the way it works is you will hold the number like that, and then you will have a photo taken. So this is your name from now on, right? So that it's anonymous. Nobody uses your information. So we will take this photo, number 1 to 100, and your work is to write a program. So basically you will start with processing this data, crop it. We will give you live images. So you know what live images are, right? So most of you who have iPhones or Samsung phones, you can take a photo and it takes like a few seconds before and after. So you have a live image. You will be given live images, and you will extract individual images from those live images. That's a very simple thing, 10 seconds so far. Then what you do is you crop those images into a specific size. You throw away the ones that look bad or blurry and you don't like them. Not all of your photos, some of them. And then you will have each images of each person into a folder. You will put them into different folders. So let's say 70 people are going to participate, so you will have 71 folders. 70 each individual number, and 1 is unknown, the ones who haven't participated. What happens in the final test of your code is I show a group photo of your class to your code, and it's going to draw a rectangle around the head of each of the people in the photo and put a number. 8, 15, 23, 75, 28, and so on. Very simple, right? So how does it work? Once you do the image pre-processing, which means cropping the images that you don't want, extracting features from those, extracting frames from the videos, putting them into a folder, you will learn in the upcoming lectures to write a classifier. What does a classifier do? A classifier says, this is an apple, this is an orange. This is person 1, this is person 2. This is person 3, this is person 4. So you train a model using convolutional neural networks, support vector machines, neural networks, whatever you like. There are a few requirements that you should do, and they are very simple. Once you have, why do you look at me like that? You're scared. So once you write that classifier, the next step is to have an object detector, face detector. It's 5 lines in MATLAB. So I will give you most of the code for your coursework. You just need to put them together. So what you need to do is, the way you're looking at me is like, so you will have the face detector in MATLAB. It detects faces. This is a very basic way of doing it. It detects eyes and noses, and basically it looks for something that is like too dark, a bit white, a bit white, a bit white, a bit dark. It's very simple, just some boxes that looks for that in the image. For those who have glasses, it gets to other features from them. Anyway. Different skin tones, different brightness images. These are all the challenges that you will see. The aim of this project is for you to have a real-life experience with computer vision from scratch. And it's a lot of fun, I hear, in the beginning. And then you will be playing with them. And if you really work on it, it's really a very, very simple project. But if you leave it to the last minute, and you don't do anything, and you decide, okay, I have like 2 hours now, let's do this, then you will be in trouble. Yeah. So it is unfortunately 50% of your final mark. I try to make it more, but it doesn't work like that here. It's a very complicated process. So it is 50% of your final mark. 50% is going to be an exam. The coursework is slightly different between undergrads and postgrads. For postgrads, you will need to detect this number as well. So if I show you an image of mine as a test image, which you haven't seen before, I just hold a few of those images for myself and give you the rest. If this image hasn't been seen, you will be asked, what number is this? And your code should detect 1, 5, 18, whatever number, right? That a specific person is holding. For undergrads, you will find the face, which is 5 lines of MATLAB. and then you will make it funny. So like Snapchat filters, like put ears around it, find where the eyes are, put on glasses, things like that. Very simple, right? So this is a very fun project, given you start soon, not leave it to the last minute. And tonight we are going to take the group photo. Abby should maybe here anyway, but yeah, we have enough. How many of you have cameras that have live mode? Like, yeah, okay, plenty, yeah. And you have enough space, like 500, 600 megabytes? Good. So the more images you have, you will thank me later. You will be happier. So we will take photos tonight. I will give you, like, it will be uploaded on Moodle. You will see this. I was offering you a group coursework. You said no. So you will have the option to opt in or opt out of this. If someone, for any reason, doesn't want their photos to be in this, you are absolutely, you have the freedom to skip it, but it doesn't mean you won't be doing the coursework. You will be enjoying your classmates' pictures. So I would suggest that you do it, all of you, and we will just take the photos now, and next week we will talk about filtering images, feature extraction, convolution, edge detection, and corner detection, and things like that. So after we take the photos, the group photos here, we will go to ELG 6 and 7, and while the rest of us are doing the lab, we will take individual photos of everyone. So we will stand in front of a plain background wall, holding the number, a few mugshots, and then that's it. All right. So if anyone doesn't want to be in the photo, please leave now and wait in ELG 6. The rest of you just say cheese. Is anyone leaving or no?